Hi, everyone. Today, our presentation is going to be called Predicting Disease Prevalence Due to Climate Change. And the three of us we're with Milliman. Meseret is the managing data scientist, and Kailey and I are GIS analysts. Raquel gave us that introduction a little bit earlier. And today, we're going to be talking about wildfires. Wildfire and its effects on human health, specifically wildfire air quality. So we'll be talking a little bit about wildfire smoke, its effects on air quality, then heat intensity, modeling data, and our model results, initial model results. This research has been sponsored by the Society of Actuaries. The work is still ongoing. This presentation is going to focus a little bit more on like our ongoing methodology as opposed to the published results, and is intended for education purposes only. So like I was saying, today we're going to be talking about climate change and wildfire. As you know, wildfire is an important natural component of many ecosystems. However, as climate change makes conditions in the US drier and hotter, wildfire intensity and extent is increasing. The average burn area of fires is increasing, and this is leading to more wildfire smoke days. So then the question kind of becomes, how does increasing intense wildfire seasons affect human health? Wildfire smoke releases gaseous pollutants, hazardous air, water vapor, and particle matter into the air. And we find that fine particulate matter, known as PM 2.5, for the diameter of the particulate being less than 2.5 nanometers, in wildfire smoke has been shown to be more detrimental to health than PM 2.5 from other sources. And so we fall into this feedback loop of increased temperatures lead to shortened melting seasons, which leads to extended fire seasons and overall decreased air quality in certain times of the year. To quantify wildfire, to turn into data that we can like count, quantify, and process, we're going to be using wildfire proxies. The first is going to be a heat index, which Kailey will be talking a little bit about later. In this heat index, we're going to be finding 30 years of continuous heat data all across the US. And then we're also going to be exploring negative air quality by using the measure of particulate matter 2.5 across the past 6 years from daily data collected from eRA monitoring stations. This map of the US, the blue dots are all representing eRA quality stations. The workflow for air quality is that we do this data collection from each state daily. Then we can interpolate the measure of 2.5 across areas that have less coverage of monitoring networks. Then we can categorize the level of PM 2.5 into unhealthy, very unhealthy, moderate, and good. And then we can aggregate these counts monthly to determine the number of days per month that have poor air quality. And here on our left, we see the US AQI level. We can explore that the PM 2.5 correlates directly to these different moderate, unhealthy for sensitive, unhealthy, very unhealthy, and hazardous, and the respective health recommendations. And we can see over the past several years how the average days kind of overall spike up in 2021. So we're seeing an increase in those negative days. And now Kailey's going to talk a little about heat intensity.
Awesome. Thanks, Nia. Yeah, so like Nia mentioned earlier, in order to look at this heat index or heat intensity, we end up downloading over 30 years of daily weather data. So it's like a ton of data. It's over a terabyte of data. In order to calculate heat intensity, we actually combine minimum daily temperature, and vapor pressure to get this heat statistic apparent temperature, which just incorporates both heat and humidity. So once we have our daily apparent temperature, we can calculate the heat intensity. And so this is done by calculating the difference between our daily apparent temperature and this historic baseline. So we're actually only looking over summer months, so May through September, because these are the months where wildfires most commonly occur. And so we take data between 1980 and 2010 to establish this historic baseline. And once we difference the daily apparent temperature from that historic baseline, we get heat intensity. And what we ultimately do is aggregate everything to the CBSA level. They're like counties or super counties. And we get the average heat intensity by each CBSA for all of our different months, our summer months May through September in the years that we're focusing on between 2017 and 2022. And this is an example of what that process sort of looks like. So what we're looking at are all of the CBSAs in the state of North Carolina. And so if we look at the figure labeled number 1, we calculate our heat metric, we calculate apparent temperature. So this image shows an example of our raster data, which is our heat data. So this is at a 1 square kilometer resolution. We downloaded this. It's freely available for the entire United States and some other regions from DayMet. And after we calculate the apparent temperature, we aggregate this by CBSA. We find the average apparent temperature for each of these regions that are shown in the black outlines. And then we can compare to the historic baseline. So basically differencing the values in images 2 and 3 to finally get our daily heat intensity data, which is shown in image 4. And so you can see some portions of the state actually have, a negative value represented by these blue polygons. And those are areas where the apparent temperature for that day is it's not as hot given the historic baseline. But other areas, like in the center of the state, were hotter on that day than they had been for that 30-year baseline period. Yep. And so overall, I show here some examples of what the data aggregated at the CBSA and monthly timescales look like. So we're looking at our summer months 5 through 9 across in the rows and for years 2017 through 2022. And so you can see that the heat data varies very regionally. But in general, if you focus on the dark red areas, as we move from 2017 to 2022, we can see generally the heat intensity is increasing for all of these regions. But of course, if you pick out specific areas, you might see different trends. But like generally on average, we see those heat intensity levels increasing. And then we have a graph of this heat intensity data by year for 4 separate regions. And so, like I mentioned, the trends do vary significantly by region. On average, we see that the West has faced greater above average heat intensity, and the West is in that bright blue line. The Northeast and the Midwest, the orange and the dark blue lines, had significant fluctuations, and the South remained relatively stable, except for a dip in, except for a dip in 2021. So overall, 2022 shows an increasing above average heat intensity for most of the regions, which indicates a shift, with the Midwest having the highest heat intensity for this year. But yeah, it's going to fluctuate since the United States is so large. It's going to vary significantly by region. And now I think Meseret will introduce her portion.
Thank you. Thanks, Mia. Thanks, Kailey. Now I will go through the modeling aspect of the project. First, I want to explain study year because as you can see on this diagram, it's different from calendar year. One study year runs from February of a given calendar year through January of the following calendar year. In addition, as shown on this slide, We divided each study year into pre-season, high season, and post-season. Pre-season consists of months from February through May. High season consists of months January through September. And finally, post-season consists of month October through January. We did this because we wanted our model to capture distinct impact of climate change during the high wildfire season, as well as the pre and post wildfire seasons. We also made sure that there is equal number of months in each season, so our aggregated values don't end up being uneven. The next concept that I want to explain is seasonal lag. In addition to the actual climate values that me and Kailey described earlier, we also calculated lagged climate values, as climate changes often have a delayed impact on our health. Therefore, we calculated up to 2 prior years of climate values for a given season. For example, for 2022 season 1, lag 1 is defined as 1 season prior to current season, and lag 2 is 2 seasons prior, and lag 3 is 3 seasons prior, and so on. Now let's talk about the details of our modeling data. First, we pulled claim encounter and enrollment data from one of Milliman's proprietary database. And we also incorporated Milliman's MARA risk score to account for comorbidity. Then we brought in climate variables, both the original values and the lagged values. In addition to that, we pulled in publicly available social vulnerability index, SVI. SVI refers to factors like poverty, lack of transportation, and crowded housing that makes communities more affected by disaster and disease outbreaks. The SVI tool is a tool that helps identify and measure these vulnerable communities. Finally, we aggregated all indicator variables at core-based statistical area, CBSA, and predicted prevalence rate per 1,000 for circulatory, respiratory, mental, and behavioral conditions. Those are our target variables. Now, I want to explain the specific machine learning model that we trained. It's called the gradient boosting machine algorithm, GBM. It's a popular algorithm in machine learning for classification and regression models. It's an ensemble learning method which trains the model sequentially, and each new model tries to correct the previous model. Next, we extracted SHAP values from the trained models and summarized the values by state. SHAP values estimate the contribution of indicator variable to the final prediction, including its interaction to other features. And they measure overall importance of a feature compared to others. So features with the positive SHAP values positively impact prediction, while those with negative values have a negative impact. The magnitude is a measure of how strong the effect is. Okay, then we calculated average of these SHAP values that I explained earlier and displayed the values on the map of United States. The SHAP values indicated in red are high SHAP values that shows high contribution to the final prediction, while the lower values are shown in green. For example, in 2019, the PM 2.5 labels had a low impact on respiratory disease prevalence rate across most states, except few Western states like Hawaii and California. As you can see here, most states are green, except few on the West and Hawaii having shades of red. And when we switch to 2022, however, we can see that most states changed color from green to different shades of red. This indicates that PM25 labels show a significant impact on respiratory conditions. The second set of maps that I am going to show are impact of heat intensity. In 2019, the elevated heat intensity that Kailey described earlier shows that there had a low impact on respiratory disease across most states except the Midwest and Southern states. So mostly we see greens like on the west side and the south. But when we switch to 2022, most states were highly impacted by excessive heat, except some states in the Northeast. Now let's look at the circulatory system. As you can see on this map here, in 2017, PM25 labels had moderate to low impact on disease of the circulatory system across most states, especially in the Midwest. When we switch to 2022, prevalence rates in most states were highly impacted by PM25 labels. And this is the heat intensity label. In 2019, we see a lot of red, a lot of green colors across the United States, except some Midwest areas. But when we switch to 2022, the prevalence rate for circulatory disease in most states were highly impacted by PM25, except so few states in the Northeast. Here, this is the last target variable that we looked at. It's for mental health and behavioral conditions. As you can see, in 2017, the PM25 labels had moderate to low impact on mental health across most states. But when we switch to 2021, we can see the prevalence rate being highly affected by PM25 labels. And this is another map for the same mental and behavioral disorder. In 2017, lots of states were green. But when we switched to 2022, the prevalence rates across the US were highly impacted by the excessive heat that are indicated by red color. So to summarize, machine learning really can be used to explore climate issues, and social determinants of health also plays a role. Climate change is a very complex issue, and interdisciplinary collaboration is essential. More research is needed to understand the total health effects of climate change. I believe that concludes our presentation. If there are any questions at this point, we can take questions.
Excellent, very sharp on timing. Great, thank you so much.